Hello and welcome back everyone. I am Shivani Garg, Assistant Professor from IIMT University Meerut. In previous lecture we have studied about the transient time response analysis for first order system. In this particular lecture we will be studying about the time response analysis for second order system. So let's start today's lecture. So what is the second order system? When we have the system with two poles, So system with two poles are called the second order system. Example, a series RLC circuit is an example of second order system, and also a mass spring damped system is also an example of a second order system. The transfer function for RLC circuit is equal to 1 upon S square SRC, as the highest power of S in the denominator is 2. So this is called the second order system. Similarly, for mass damper system we have the transfer function as 1 upon ms square plus bs plus k. Here also the maximum power is 2. So this is also a second order system. So in general the transfer function of any second order system can be represented by b upon s square as plus b. So to study and understand the response of second order system, its transfer function is written in terms of certain system specifications. So let's see what are these. So this is the standard second order system block diagram. Here we have an input Rs, we have a feedback Hs which is equal to 1, and a forward gain Gs is equal to omega n square upon S into S plus 2 zeta omega n, and output Ys. Using the same transfer function for feedback, Ys upon Rs is equal to Gs upon 1 plus Gs Hs. We get the transfer function as this using this formula. This is the standard form of transfer function for second order system. Here omega n is called the system's natural frequency, and this is zeta, which is called the damping ratio, system's damping ratio. So system damping ratio zeta is a dimensionless quantity which describes the decay of the oscillation during a transient response. It is the ratio of actual damping to critical damping, and omega n is the natural frequency. It is the angular frequency at which the system oscillates in the absence of damping force. System damped frequency, it is the angular frequency at which the system tends to oscillate in the presence of damping force, and which is equal to omega d is equal to omega n under root 1 minus zeta square. So for response of the second order system mainly depends upon the value of zeta. For any test input, the response of second order system can be studied in 4 cases depending upon the damping effect created by the value of zeta. So first case would be zeta is greater than 1. So this system is called the over damped system. When zeta is equal to 1, it is called a critically damped system. When zeta is in between 0 and 1, it is called the undamped system. And when zeta is greater than 0, so this is greater than 1 equal to 1, if it is equal to 0, so if zeta is equal to 0, the system is called undamped system. So here we do not take zeta as negative value, because when zeta is negative, the oscillation tends to increase, which makes the system unstable. So we only consider the 4 cases when zeta is greater than 0 or equal to 0, because we are not considering the case with unstable system. So damping and type of damping. Damping is an effect created in an oscillatory system that reduces, restricts or prevents the oscillations. So what does damping do? It reduces or restricts or prevents the oscillation in the system which may be caused by the disturbances. So first one is the overdamped system. When the transient response exponentially decays to steady state without any oscillation, it is called the overdamped system. Critically damped system, it is similar to overdamped system, but the time constant is higher, or the oscillations would be decays in shortest possible time. Another one is underdamped system. In this the system transients oscillates with the amplitude of oscillation gradually decreases to 0. Another is undamped system. Here the oscillation does not tend to reduces 0. It keeps on oscillating at the natural frequency of oscillation without any decay. So this graph represents what kind of damping we have. We have first one, for zeta is equal to 0 we have undamped system. Okay, for zeta is equal to 1 we have critically damped system, and for zeta is greater than 1 we have overdamped system, and for zeta in between 0 and 1 we have underdamped system. So as you can see, for undamped system we have oscillations. These oscillations are not decaying and it will keep on oscillating at till the time of infinity if we do not have any damping. And then when zeta is equal to 1, the purple line shows the critically damped system. It does not have any oscillation and it decays at a shortest possible time. This time is minimum for this particular system in any compared to other damping. When zeta is greater than 1, the system is called overdamped. It takes the most time to remove the oscillation, to reach the system to the its output value without any oscillation. And another one, when zeta is in between 0 to 1, it is called undamped system, where it has some oscillations but it will be decayed after a certain period time of. So let's see the response of second order system for standard input. So first one is for impulse input. As we already studied, the Laplace transform of impulse input is Rs is equal to 1. So from the equation we have Ys upon Rs is equal to this omega n square s square upon zeta 2 zeta omega ns. So if we put this here, R into Rs and R, which is equal to 1, so this would become again this one. So let's see, consider all the cases for values of zeta. So when zeta is equal to 0, it is called undamped system. So what we get Ys is equal to omega n square upon s square plus omega n square. So if we take the inverse Laplace transform, we get Yt is equal to omega n sin omega nt. So if we can see, with sin omega nt at infinity also it would oscillate at a sinusoidal wave. So what we are getting, so if this is 0, this is t, so this would be like this, and this is your omega n and this is minus omega n. So it will keep on oscillating at a natural frequency omega n. So let's see another case 2, when zeta is in between 0 to 1, which is called the underdamped system. So let's see, Ys is equal to omega n square s square to zeta omega ns plus omega n square. If we take the inverse Laplace transform, we can simply factorize this into two roots, which is equal to s plus zeta omega n j omega t, where omega d is equal to, as we have already known, omega n under root 1 minus zeta square, and similarly s plus zeta omega n plus j omega d. So we have here a complex conjugate roots. If we take the Laplace inverse transform, we get omega n under root 1 minus zeta square omega d upon s plus zeta omega n whole square plus omega d square. So the inverse Laplace transform Yt would be equal to omega n upon under root 1 minus zeta square into e to the power minus zeta omega nt sin omega dt. So for impulse system, we have this input, this Yt as omega n upon under root 1 minus zeta square e to the power minus zeta omega nt sin omega dt. So here we have for underdamped system, we will have this kind of output. This due to this e to the power minus zeta omega nt, this term would get vanished at the infinity, but initially it would have some oscillations and finally it would decays to 0. So let's see another example. For case 3, when zeta is equal to 1, it is called the critically damped system. So we put zeta is equal to 1, we get s is equal to omega n square s square plus 2 zeta omega ns plus omega n square, which is this term is equal to s plus omega n whole square. So if we take the inverse Laplace transform, we get Yt is equal to omega n square t e to the power minus omega nt. So the output would be, we have t, we have this yt. So we will get this kind of, without any oscillation it would tend to 0. Okay, so there will not be any oscillation as no sine or cos term is here. We have in e to the power minus omega nt, which would become 0 at t is equal to infinity. So we will get this output. Okay, so next case 4, when zeta is greater than 1, it is the overdamped system. Again we have is equal to omega n square s square plus 2 zeta omega n s plus omega n square. Here as zeta is greater than 1, so we have a real roots instead of complex conjugate loop as in case of underdamped system. So when we take the inverse Laplace transform, we get yt is equal to omega n upon 2 under root zeta square minus 1 e to the power minus zeta omega n minus omega under root zeta square minus 1 t minus omega n 2 under root zeta square minus 1 e to the power minus zeta omega n plus omega n zeta square minus 1 t. So if we see with these two terms would become 0 at infinity, and initially it would be there. So what we get, we will get the output as t y t. We will have the same output as in critically damped system, but it would be somewhat slow. It would take more time to reach the 0 value. So these were the case of the 4 cases for 4 values of zeta with impulse input. Now let's see with the unit step input the response of second order system for different values of zeta. So as we know, the Laplace transform for this is Rs is equal to 1 by s. So the ys would be equal to omega n square s into s square plus 2 zeta omega ns plus omega n square. So let us consider again the 4 cases. First case, zeta is equal to 0. For undamped system, ys would be equal to omega n square upon s square plus omega n square. If we do the partial fraction, we get 1 upon s minus s upon s square minus omega n square. So we get yt is equal to 1 minus cos omega nt. So if we see this, because of this term, this will not get vanished at the time of infinity. There will always be some oscillations, and we get the graph like this. So we will get the graph like this. So it will oscillate around the value 1. So another case, when zeta is 0 to in between 0 and 1, so it is called the underdamped system. Again we have a complex conjugate roots. We can do the partial fractions. Okay. So if we take the inverse Laplace transform, 1 by s minus s zeta omega n s plus zeta omega n whole square plus omega d square minus zeta omega n, this is omega d under root 1 minus zeta square under root 1 minus zeta square, this would get cancelled out. So s plus zeta omega n whole square plus omega d square. So if we take the inverse Laplace transform, yt would be equal to 1 minus e to the power minus zeta omega nt cos omega dt minus zeta upon under root 1 minus zeta square e to the power minus zeta omega n sin omega dt. So or yt would be equal to, if we further simplify this equation, we get yt is equal to 1 minus e to the power minus zeta omega nt upon under root 1 minus zeta square, and we can simply keep the terms in bracket, 1 minus zeta square cos omega dt plus zeta omega n omega dt. So if we see, we can convert this into sin c plus d form. How we can convert this? We can simply assume cos theta is equal to zeta. Let cos theta is equal to zeta, then sin theta would be equal to under root 1 minus zeta square. So this would be your sin theta and this would be your cos theta. So if we see, this is sin theta cos theta, sin theta cos theta 2, cos theta sin theta 2. So this would become sin cos theta plus. So here we have sin theta cos omega dt plus cos theta sin omega dt. So this can be written in terms like this, omega dt plus theta sin c plus d. It is the formula for sin c plus d. So where theta is equal to cos inverse zeta or cos theta is equal to zeta, which is equal to sin inverse under root 1 minus zeta square. So if we draw the response for this particular system, we get this is t, this is yt, so this is 1. So for because of this signed term we have some oscillations, and because of this e to the power minus zeta omega nt, these oscillations will decay at the time at t tends, when t tends to infinity. So it will start from here, it will have some peak value, it will have some oscillations, and then it will decays to, it will settle out at value 1. Okay, so this whole term would become 0, and the final value would be at time steady state yt would be equal to 1. So next case 3, when zeta is equal to 1, that is for critically damped system. So ys would be equal to omega n square s square plus 2 omega ns, as zeta we have kept 1, or plus omega n square. So we take the Laplace inverse transform for this particular function, and then we do the partial fraction. We get 1 upon s minus 1 upon s plus omega n plus minus omega n upon s plus omega n whole square. So the inverse Laplace transform would be equal to yt is equal to 1 minus e to the power minus omega nt minus omega nt e to the power minus omega nt. Okay, so if we see from this term would get vanished at the time when t tends to infinity, and this will also get vanished when t tends to infinity. We would have only this term. So these two are the transient terms, and this is the steady state term. So when we draw the response, we get this is t and this is yt, this is 1. So what we get a critically damped system. It will not have any oscillation because it does not have any sine or cos term. It will simply have a exponential curve. It will be settled at one value after some point of time. Okay, so next one is when zeta is greater than 1 or over damped system. So here ys is equal to omega n square upon s square plus 2 zeta omega ns plus omega n square. As zeta is greater than 1, we will have the real roots, which so y2 would be equal, ys would be equal to omega n square upon s square plus 2 zeta omega ns plus omega n square s. If we take the inverse Laplace transform by using the partial fractions system, we get yt is equal to 1 minus 1 by 2, 1 plus zeta upon under root zeta square minus 1 into e to the power minus zeta omega n minus omega n under root omega n square minus 1 t plus 1 by 2 zeta upon under root zeta square minus 1 e to the power minus zeta omega n plus omega n zeta square omega n t. So if we see from this term would get vanished because of this e to the power at t tends to infinity. This whole term will also get vanished at t tends to infinity. We will have only this term. Okay, so this is your steady state value, and these two are your transient values for the particular system, transient response. So when we draw the response, we have t, we have 1 by t. So how we will get, this is the overdamped system, so it would take some time, greater time than to reach the value 1. So this is the this is the response of second order system for overdamped system. So this is it for this lecture. In this particular lecture we have studied about the transient response of second order system. In next lecture we will be studying about the design specifications of time response analysis for second order systems. Thank you so much.